Okay, we're going to finish up by talking a little bit about different approaches to dealing with needing to solve intractable problems. There's actually a lot of different ways to proceed when you run into an intractable problem. One idea is to exploit it. So in fact, an example of this, a very successful example of this, is modern cryptography. And people using the internet for commerce or for interaction through digital signatures and other mechanisms are absolutely relying on modern cryptography for security and privacy. And that's all based on the RSA crypto system, or much of it. And it's based on the idea that multiplying two n-bit integers is relatively easy. This brute force multiplication algorithm gets it done in quadratic time, and there's faster ways. So that's polynomial time. In order to encrypt something, you need to multiply things. But in order to break something, you would need to factor things. So that's exploiting intractability. Nobody knows a good way to factor. A factor is not NP-complete, by the way, not known to be NP-complete. It doesn't. It's not quite as hard as other problems, but still, nobody knows a fast way. So this is an example of exploiting a problem that's suspected to be intractable. In fact, there's other ways to make money. Ravesh, Shavir, and Edelman put up some challenges, and go ahead and factor this number. It's worth $30,000. Some of these things have been prizes have already been claimed, but it's maybe easier to go after this than after the million. Actually, Ravesh, Shavir, and Edelman were but they were professors at MIT when they came up with this, and they realized that the important commercial potential of this, and actually created a company based on the difficulty of factoring that sold for $2.1 billion not that long ago, and it's the basis for internet commerce. These possibilities for making a lot of money out of understanding the difficulty of computation are not imaginary. They're quite real. I talked briefly about the complexity of factor. That's another problem like LP. Its current status is what LP was in the 70s. We were using it. A lot of people were doing it. We knew that the worst case of simplex was exponential. Would like to classify. I'd like to know if there's a polynomial time algorithm, but nobody knew one. And then the big surprise for LP was that Katchin came up with a polynomial time algorithm, and then people went to work. For factor, we're kind of in the same situation. It's in NP, as we saw, it's just a search problem, but it's not known or believed to be either NP or NP-complete, but again, who knows? What if it turns out that P equals NP? So that would mean that factors NP, and that would, it's not just the math, that would mean there'd be an easy way to break the RSA crypto system, which is in wide use. People could break codes just by factoring, and that would not be a good thing for the modern economy. Actually, something that attracted a lot of attention, although it's almost 20 years ago now, was a result by Peter Shor that said that there's a device, not quite a real device, called a quantum computer, at least one that you could imagine building, that solves factoring in polynomial time. That raises the question of, do we still believe the extended Church-Turing thesis? And there are plenty of people that are not so sure and are working hard on trying to build devices that might have a big impact on this kind of theory. Well, actually, it would create and has created a new theory based on how difficult is it to do things with these sorts of devices. Okay, but in general, suppose you have an intractable problem. What are you going to do to cope with it? Well, there's a number of things that people have done really successfully. So remember what it means to be intractable. So problems intractable if in the sense that we don't know a polynomial time problem that's guaranteed to solve any instance. Now, so maybe you can give up on one of the three key features of that statement. Maybe we don't care if we can solve every possible instance. Maybe it's only the instances that are going to arise in the real world that matter. Or maybe you can even simplify the problem, and that's the one that you really need to solve. So, for example, if you restrict satisfiability to have at most 2 literals per equation, you can solve in linear time. Or even if you just insist that there be at most one of the literals per equation be not negated, that's called a Horn set. There's a linear time algorithm for that. So maybe your problems, you're trying to solve too hard a problem, and you can come up with a more special case of the problem that's actually the one you want to solve that you could solve. So that's definitely one way to cope with intractability. Another thing is optimality. We've been talking about search problems, but this is more a statement about about optimization problems where we're looking for the best solution, or you're looking for approximate solutions, where you take away the guarantee that the solution is perfect in some way. So, for example, the traveling salesperson problem, people can find ways to get tours that are close to the best possible tour, but maybe not the best. And there's many, many other examples of this, where people are looking for good solutions without trying to guarantee that they're optimal. And those maybe those solutions are very close to optimal, or at least close enough that you can use the solution and move on. If you can understand the quality of the solution that you have, that might be good enough. And again, the idea of approximation algorithm where you really can prove what the quality is. So, for example, there's a max 3 set that guarantees to satisfy 7/8 of the clauses. And actually, these algorithms, they're really coming at a fine line between what's tractable and intractable. And so, for example, if you want to do 7/8 plus anything, then it means that P equals NP. If you can do that in polynomial time, P equals NP. There's lots and lots of amazing results of this sort out there. But anyway, in practice, relaxing the condition that you find the perfect solution sometimes can get a long way in practice. And then the other thing is guaranteed polynomial time. Now, we're talking about worst case behavior, but there's solutions out there. For example, there's a SAT solver that was done here at Princeton that can solve 10,000 variable SAT instances. Or as I mentioned, there's solvers out there for integer linear programming that will solve huge instances of real world problems. Worst case behavior may not be observed in the real world, might even be hard to find real world problems. So there's definitely a lot of room here to find solutions that might be efficient for the class of problems that you want to solve. And I just want to finish up with one of the most famous NP-complete problems, which is the so-called Hamilton path problem. And so that's given a graph. You want to find a path that visits every vertex exactly once. And simple path, so I can't reuse any edge. So that's a solution to the Hamilton path problem for this graph. Another way to characterize it is a longest path problem, longest simple path problem in a graph. If you want to visit every edge exactly once, that's not difficult. It's actually in the book, but Hamilton path is NP complete. So that's a natural problem that's NP complete. And actually, this is it's NP complete, but here's a really simple exponential time algorithm for computing the Hamilton path. It's just our depth of first search algorithm where we mark nodes and recursively go through all the edges, all the vertices adjacent to the current vertex, and if they're not marked, go ahead and visit them recursively, marking all the nodes that we see. The only difference from the depth first search is this thing here, where when we're done with our recursive call on a node, we unmark it. And what that does is make this code try all possible paths, and there's an exponential number of paths. So it's a fine program for doing it for small graphs, but it's going to take exponential time for big graphs. But the longest path problem is NP complete, and we're going to finish up with a song that was composed by a Johns Hopkins student one time when he was having trouble thinking about this idea.
Find the longest path. Whoa, find the longest. If you said P is NP tonight, there would still be papers left to write. I have a weakness. I'm addicted to completeness, and I keep searching for the longest path. The algorithm I would like to see is of polynomial degree, but it's elusive. Nobody has found conclusive evidence that we can find the longest path. I have been hard working for so long, I swear it's right, and he marks it wrong. Somehow I'll feel sorry when it's done. GPA 2.1 is more than I hope for. Gary Johnson, Karp, and other men and women try to make it order and log n. Am I a mad fool if I spend my life in grad school, forever following the longest path? Whoa, find the longest path. Whoa, find the longest path. Whoa, find the longest path.
That's a fine sentiment on which to end this class on algorithms. I hope that all of you out there are inspired to face the computational challenges of the future with the algorithms and the concepts that you've learned in this class. So that's all. Keep searching. So long.